In the previous video, I showcased the Matlab simulation of a grid-connected inverter with a passive damping scheme. Additionally, I elaborated on the process of designing the damping circuit. Because the passive damping circuit employs resistors in the circuit, power is dissipated in it, potentially impacting the efficiency of the inverter. Therefore, in this regard, active damping proves superior to passive damping. So in today's video, I am demonstrating how to simulate a grid-connected inverter with an active damping scheme using Matlab. Let's get started. Now I'll provide you with the LCL filter values used in the simulation. I won't go over the design of the LCL filter here because I've already covered that in one of my previous videos. The inverter side inductance value is 3.6 mH, the grid side inductance is 1 mH, and the capacitance is 4.7 microfarads. We can calculate the resonant frequency of the filter from these values using the equation, the square root of L1 plus L2 divided by L1 L2C. After substituting the values, we find the resonant frequency to be 2624.37 Hz. I'll use this value during the simulation. This is the block diagram for synchronous reference frame control used in the simulation. I covered the controller's details in one of my previous videos, so you can refer to that for a deeper understanding. I will now demonstrate how to modify the controller to incorporate the active damping logic. The majority of the control components will remain unchanged, with only a few adjustments needed. In addition to sensing grid voltage and current, we also require sensing the LCL filter capacitor current. This current needs to be converted from the ABC frame to the alpha-beta frame. All other voltage and current transformation blocks, as well as the current control loop, will remain the same, except for the block following these voltage signals, VD and VQ. The VD and VQ voltage signals are then transformed into alpha-beta voltages. From these alpha-beta voltages, the product of the gain and the capacitor alpha-beta currents is subtracted. This method is similar to connecting a resistor in series with the capacitor, but there's no physical need to connect the resistor in the system. The gain value of K here is analogous to the resistance value used in the passive damping method. For this reason, this method is typically referred to as the virtual resistance damping scheme. Now, after subtracting the capacitor current signals, the voltages are transformed into the ABC frame, and the PWM signals are generated. This completes the control logic. Now, let's open Matlab and begin the simulation. Add an IGBT. Create three-phase H-bridge using IGBTs. Uncheck this box. Add an IN port. Name it as PWM1. Connect the port to the gate terminal of all the IGBTs. Add a connection port. Name it as VDC+. Copy the port. Name it as VDC-. Connect the ports to the positive and negative ends of the H-bridge. Copy the port. Name it as VR. Keep the port location right. Copy the port. Name it as VY. Keep the port location right. Copy the port. Name it as VB. Keep the port location right. Create a subsystem from the selection. Delete all the signals. Add a DC voltage source. Connect it to the H-bridge. Set the voltage 800.
Add a from block. Name it as PWM1.
Connect it to the subsystem block, and similarly add other PWM signals also.
Name it as PWM2. Name it as PWM3. Name it as PWM4.
Name it as PWM5. Name it as PWM6.
Add a current measurement block.
Connect to all the three phases.
Add a go-to block.
Connect to the measurement block. Name it as IR. Name it as IY. Name it as IB.
Add a series RLC branch.
Set branch type, L, and value 3.6 mH. Connect it in all the three phases. Copy the RLC branch. Set the branch type, RC, resistance 0.002, capacitance 4.7 microfarad. Connect it in all the three phases. Copy the RLC branch. Add a three-phase I measurement block. Set the parameters. Connect to each inductor.
Add a demux.
Set the number of outputs 3.
Add a go-to block.
Name it as VR. Name it as VY. Name it as VB. Add a three-phase voltage source. Flip the block left-right. Connect to the measurement block. Set voltage 400, phase angle 0, frequency 50, source inductance and resistance very small values, and base voltage also 400. Now drag and drop the voltage signals. Add a mux. Set number of inputs 3. Add AABC to alpha beta block. Add a alpha beta to DQ block.
Add a go to block.
Name it as alpha beta.
Add a from block.
Name it as omega t.
Add a demux.
Set the number of outputs 3.
Add a go to block. Copy the go to block.
Name it as VD. And name it as VQ. Copy the entire block. Delete the alpha beta signal, and change input signals from VR, VY, VB, to IR, IY, and IB. And change output signals from VD, VQ to ID and IQ. Add a alpha beta to DQ block. Connect alpha beta signal to the input.
Add a demux.
Set number of outputs 3.
Add a sum block.
Connect to the second output of demix.
Change its sign to plus minus. Add a constant block.
Set the value 0.
Add API controller.
Make controller type PI, and set the values of KP and KI.
Add an integrator.
Add the output of integrator to the omega t signal point of the transformation block.
Add a go-to block.
Name it as omega t. I forgot to change the value of these inductors. Set all the three inductor value, 1 mH.
Add a constant block.
Set the value -40. And that is the reference value of the grid current.
Add a sum block. Change its sign to +-.
Drag and drop the ID signal.
Add APID controller.
Make controller type PI, and set the values of KP and KI. Add another sum block.
Add a gain block.
Set the gain value, 2 into pi into 50 into 4.6 a power -3. Now drag and drop the IQ signal.
Copy the sum block.
Now drag and drop the VD signal.
Add a go-to block.
Name the signal ED. Add another constant block. Set the value 0.
Copy the sum block.
Connect IQ signal to sum block.
Copy the PID controller. Copy the sum block. Copy the gain block.
Connect ID signal to gain block.
Copy the sum block.
Connect VQ signal to sum block.
Copy the go-to block.
Name it as EQ. Drag and drop ED and EQ signals. Add a mux. Set number of inputs 3. Add ADQ to ABC transformation block. Connect omega t signal to the block.
Add a demux.
Set number of outputs 3.
Add a gain block.
Set the value 2 by 800.
Copy the gain block. Add a relational operator. Change the operation to greater than or equal to. Add a repeating sequence.
Set the time and output values for 10 kHz, -1 to 1, triangular carrier signal. Connect this block to relational operator.
Add a logical operator.
Set the operation not. Connect this block to relational operator. Now connect all the outputs to the PWM signals of the IGBT. Now copy all the voltage and current signals.
Add a scope.
Change the scope settings. Connect voltage and current to the scope.
Add a power guide block. Set simulation type discrete and sampling time 1e raised to -6. Open the model settings.
Choose fixed step solver type. And step size 1e power -6.
Set simulation time 1 second and run the simulation.
Open the scope to view the grid voltage and current. This is the voltage and current, and the grid current amplitude is same as the reference value. So the controller working fine. Now we will see how to excite the resonance in the inverter. To do that, we need to inject a voltage of a certain magnitude with a frequency same as the resonance frequency of the LCL filter. First I will copy the three-phase source. Connect this source in parallel with the existing source. Set the voltage 20, frequency 2624.37 Hz, which is same as the resonant frequency of the filter.
Now run the simulation again.
Open the scope to view the grid voltage and current. Here you can see that, after introducing the resonance, the grid current looks highly distorted with lots of high-frequency component present in it. This shows the challenge posed by resonance in grid-connected inverters. To address this issue, it's necessary to incorporate damping into the system. To implement the active damping scheme, we must adjust the control algorithm. I'll demonstrate how to do this now. First I will make some adjustments here. Delete the connection here.
Add a current measurement block.
Connect it in series with the capacitors.
Add a go-to block.
Name it as IC1.
Copy the go-to block.
Name it as IC2. And name it as IC3. Connect it to the measurement block. Now we need to convert this capacitor current from the ABC frame to the alpha-beta frame. So copy the current signals first. Copy the mux. Add AABC to alpha-beta block. Copy the demix.
Add a go-to block. Copy the go-to block.
Name it as ICA. Name it as ICB. Delete the transformation block and omega T signal. Move these blocks to the right side. Add a DQ0 to alpha-beta block. Copy the omega T signal. Copy the demix.
Add a sum block. Change its sign to plus minus. Copy the sum block.
And connect to the Dmax.
Add a gain block. Copy the gain block.
Set the value 10. Connect the capacitor currents to the gain block. Connect the output of gain block to the sum block. Copy the mux. Connect the output of sum block to the mux. Add a alpha beta to ABC block. This completes the modification in the control logic. Now we can run the simulation. Open the scope to view the grid voltage and current. Now after introducing the damping logic, the distortion in the current has disappeared, and this is how the active damping methods work. I hope you understood the concept, and this is the end of this presentation. Thanks for watching.